In this presentation, we analyze cogeneration, also referred to as combined heat and power generation, indicated by the acronym CHP. Cogeneration represents an advanced energy conversion strategy aimed at the simultaneous production of electricity and useful thermal energy within a single integrated system. This approach is particularly relevant in the context of energy efficiency, sustainability, and decentralized energy systems, where maximizing primary energy utilization is a key design objective. In this presentation, we analyze cogeneration, also referred to as combined heat and power generation, indicated by the acronym CHP. Cogeneration represents an advanced energy conversion strategy aimed at the simultaneous production of electricity and useful thermal energy within a single integrated system. This approach is particularly relevant in the context of energy efficiency, sustainability, and decentralized energy systems, where maximizing primary energy utilization is a key design objective.
First of all, we define the concept of cogeneration, also referred to as combined heat and power, or CHP. Cogeneration is the simultaneous production of electricity and useful heat, starting from a single primary energy source. A key feature of CHP systems is that both energy forms are considered valuable outputs, and the plant operates as a single integrated unit, typically located close to the point of use. The primary energy source can be fossil-based, most commonly natural gas, or renewable, such as biogas, biomethane, solid biomass, or hydrogen. The recovered heat can be used for space heating, hot water production, or industrial process heat, including steam generation. An important operational aspect of cogeneration systems is that the demands for heat and electricity must generally occur simultaneously. Only when thermal or electrical storage systems are introduced can this coupling be partially relaxed, allowing greater operational flexibility. In conventional power generation systems, electricity is produced in centralized plants, while thermal energy is largely rejected to the environment. Only a limited fraction of the primary energy input is converted into electrical work, whereas the remaining part is dissipated as low-grade heat. This separation between electricity generation and heat production results in low global efficiency and significant energy loss.
In this slide, we introduce the concept of cogeneration. Cogeneration is based on the idea of recovering all or part of the heat that heat engine must inevitably reject during operation. Instead of being dissipated to the environment, this heat is recovered and useful in a useful way. In many cases, the recovered heat can be used in industrial applications, for example as steam, or supplied to district heating networks. Cogeneration allows a much higher overall efficiency and reduces fuel consumption, leading to lower carbon dioxide emissions. A typical cogeneration plant includes a thermal engine, an electric generator, and a heat recovery system. Cogeneration overcomes the limitations of conventional generation by recovering the thermal energy rejected by the thermodynamic cycle and reusing it for useful purposes. This slide compares a conventional power plant with a cogeneration plant. On the left, let me on the left, in a cogeneration plant, in a conventional plant, the fuel energy, e-fuel, is supplied to the engine system. Part of this engine is converted in electric energy, EL, while the remaining part is dissipated, for example, mechanical losses, thermal losses, and so on, and part is discharged as heat. This discharged heat is not recovered and is lost to the environment. On the right, in a cogeneration plant, the same electric energy is produced, but the discharged heat is recovered, is sent to a heat recovery system here, and part is recovered and can be used for industrial purposes, as district heating, for example, or industrial applications. As a result, the cogeneration improves the fuel utilization and increases the overall efficiency.
In this slide, we summarize the main benefits of cogeneration compared with the separate production of electricity and heat. The first key advantage is increased efficiency. By producing electricity and useful heat simultaneously, cogeneration systems can be up to 40% more efficient than separate generation, significantly reducing overall energy losses. Higher efficiency directly translates into lower energy costs. Because less fuel is required to meet the same electrical and thermal demand, cogeneration users benefit from reduced operating expenses. Another major benefit is the reduction of environmental emissions. Thanks to its high efficiency, cogeneration avoids a substantial amount of carbon dioxide emissions. In Europe alone, cogeneration saves approximately 200 million tons of CO2 every year, which is equivalent to the annual emissions of more than 40 million passenger cars. Cogeneration also supports renewable energy integration. It can operate using renewable fuels, and currently, about 27% of the fuels used in cogeneration in Europe are renewable, mainly biomass and biogas. In addition, cogeneration enhances energy system resilience. By generating electricity and heat close to the point of use, it provides flexibility and helps balance systems with a growing share of intermittent renewables such as wind and solar power. Cogeneration further reduces electricity transmission and distribution costs since power is produced locally, lowering grid congestion and losses. Finally, cogeneration contributes to job creation, employing around 100,000 people in Europe, with further growth expected as investments in energy efficiency and low carbon technologies continue.
This slide shows some typical applications of combined heat and power plants. CHP systems work best when electricity and heat are needed at the same time on a regular basis. In the plastic industry, and in the paper industry, electricity is used to operate machines and production lines. At the same time, thermal energy is required for heating and drying processes. In these sectors, cogeneration allows both energy demand, thermal and electric, uh, to be covered efficiently. Also in oil refineries and steel and metal industry, energy consumption is very high. Large amount of heat are needed for these industrial processes. Recovering heat in these plants leads to a strong improvement in overall efficiency. Cogeneration is also common in the ceramic, bricks, and tile industry. Here, thermal energy is essential for kilns and drying stages. Finally, also in agriculture, greenhouses are important non-industrial application. Heat is used to control the internal temperature, while electricity supplies lighting and auxiliary systems. In all these cases, CHP systems reduce fuel consumption, increase efficiency, and lower environmental impact compared to separate energy production. Here you can see additional applications of combined heat and power generation in the service and commercial sectors. In this context, CHP systems are particularly valuable because energy demand is continuous and reliable. On a university campus, cogeneration can supply electricity for classroom, laboratories, and other facilities. At the same time, recovered heat is used for space heating and domestic hot water. In hospitals, CHP systems are especially important. Hospitals require very high level of energy reliability. Electricity is needed for medical equipment, while thermal energy is required for heating, for hot water, and sterilization processes. Data centers represent another important application. They have constant demand of electricity and generate a large amount of waste heat. This heat can be recovered and reused, for example, for heating nearby buildings. In the food and beverage industry, cogeneration supplies electricity for processing and refrigeration, and heat for cooking and cleaning. Finally, airports, hotels benefit from CHP due to their steady demand for both heat and power throughout the day. In these applications, CHP improves efficiency, reliability, and energy sustainability.
In this graph, we can find a classification of cogeneration systems based on electrical power output. On the vertical axis, we have the electric power output. while the horizontal axis represents different CHP size categories. At the lower end, we find micro-cogeneration systems, typically with electrical power below 50 kilowatts. These systems are mainly used in residential buildings, small commercial facilities, or small service applications. They are designed to meet local heat demand, with electricity produced as a secondary output. Moving to higher power levels, we have small cogeneration systems, with electrical output ranging approximately from 50 kilowatts up to about 1 megawatt. These systems are commonly applied in hotels, hospitals, small industries, and commercial buildings, where heat and power demands are more significant and relatively continuous. Finally, above 1 megawatt of electrical power, we refer to large cogeneration systems. These plants are typically installed in industrial sites, district heating networks, or large energy facilities, where both thermal and electrical demands are very high. This classification is useful for selecting the most appropriate CHP technology according to the scale and application.
In the previous slide, we classified cogeneration systems according to their electrical power output. We now focus on the lower power ranges, namely small-scale cogeneration and micro-cogeneration systems. Cogeneration plants with an electrical output below 1 megawatt are generally referred to as small-scale cogeneration. When the electrical output falls below 50 kilowatts, the system is classified as micro-cogeneration. These thresholds are not arbitrary, but originate from regulatory and standard definitions, such as those provided by the European Energy Efficiency Directive and by national regulations, including the Italian framework. From a technological point of view, small and micro cogeneration systems are typically based on reciprocating internal combustion engines or microgas turbines, which are well suited for decentralized and distributed installations. A key distinction between small scale and micro cogeneration concerns the primary energy objective. In small scale cogeneration, electricity production is usually the main goal, while thermal energy is recovered as a byproduct. In contrast, micro cogeneration systems are primarily designed to produce heat, with electricity generated as a secondary output to support local consumption. Small scale cogeneration offers several important advantages. It enables the recovery of thermal energy that would otherwise be wasted, leading to fuel savings. It also contributes to lower air pollutant emissions and to a shorter power distribution chain, with a clear reduction in electrical losses. Finally, it helps reduce the need for large-scale energy infrastructure, such as centralized power plants and long transmission lines. In this slide, we describe the two main cogeneration schemes that arise from the cascade use of energy, the topping scheme and the bottoming scheme. In the topping scheme, electrical power production is the primary objective. A high-temperature thermodynamic cycle, typically fired by fossil or renewable fuels, generates electricity. The heat released by this cycle, which would otherwise be wasted, is then recovered and used as useful thermal energy. This is the most common cogeneration configuration, and it includes technologies such as gas turbines and internal combustion engines with heat recovery. In contrast, the bottoming scheme starts from an industrial process that already operates at high temperature. In this case, the waste heat produced by the process is recovered and supplied to a power cycle, which converts part of this thermal energy into electricity. Typical applications of the bottoming scheme are found in energy-intensive industries such as steelworks, glass manufacturing, and the production of ceramics and bricks. This configuration is often referred to as waste heat recovery and commonly makes use of organic Rankine cycle power plants. Overall, the choice between topping and bottoming schemes depends on whether electricity production or industrial heat demand represents the primary driver of the system.
The aim of this slide is to compare cogeneration with separate heat and power generation, focusing on primary energy consumption and overall efficiency. Let us start with the cogeneration case, shown on the left side of this diagram. With an input of 100 units of primary energy, the CHP system produces both electricity and useful heat. About 35 units are converted into electric energy, corresponding to an electrical efficiency of 35%. At the same time, 50 units can be recovered as useful thermal energy, with a thermal efficiency of 50%. Only a limited amount of energy, about 15 units, is dissipated as waste heat. Now let us consider the case of separate production, shown on the right side. To generate the same amount of electricity, a conventional power plant with an electrical efficiency of 49% requires about 71 units of primary energy. This result can be obtained dividing 35 by 0.49. To produce the same thermal energy, a boiler with an efficiency of 90% requires an additional 56 units of primary energy. Result that can be obtained dividing 50 by 0.9. As a result, the total primary energy input is approximately 127 units, equal to 71.4 plus 55.6, which is significantly higher than in the cogeneration case. This comparison clearly shows that cogeneration allows a substantial primary energy saving. By producing heat and electricity in a single integrated process, CHP systems reduce energy losses, improve efficiency, and lower environmental impact compared to separate generation.
In this slide, we introduce the main performance parameters used to characterize cogeneration plants, all based on a first law, or energy, perspective. We start with the electrical efficiency of cogeneration, which measures how much of the fuel energy input is converted into electrical energy. It is defined as the ratio between the electrical energy produced, EL, and the fuel energy input, E fuel. This parameter is particularly relevant when cogeneration plants are compared to conventional power-only generation. We then define the thermal efficiency of cogeneration, which quantifies the fraction of fuel energy that is converted into useful recovered heat. It is important to note that only the heat effectively recovered and delivered to users, Q-rec, is considered, while dissipated heat is excluded. By combining these two contributions, we obtain the energy utilization factor, or EUF, also referred to as the first law efficiency of the cogeneration plant. The EUF represents the fraction of fuel energy that is converted into useful electrical or thermal output, and it is simply equal to the sum of the electrical and thermal efficiencies. While the EUF is very useful to assess overall energy performance, it does not account for the quality of energy, but only for its quantity. This limitation becomes important when comparing electrical and thermal outputs. Finally, we introduce the cogeneration ratio, or electric index, which is defined as the ratio between electrical energy and useful thermal energy. This parameter provides insight into the operational character of the plant, indicating whether it is more electricity-driven or heat-driven, and it is particularly useful for system design and matching energy demand profiles.
In this slide, we introduce the Primary Energy Saving, or PES index. The PES index is the indicator adopted by the European Union to quantify the energy benefit of cogeneration. The PES index measures the relative primary energy saving achieved by a cogeneration system compared to an equivalent reference system that produces the same useful outputs, namely electricity and useful heat, using separate conventional technologies. In other words, we compare cogeneration with a reference case in which electricity is generated in a conventional power plant and heat is produced in a boiler, assuming that the electrical energy and the useful heat are identical in both cases. If we denote by F the fuel input to the cogeneration plant, and by F sub SP the total primary energy input required by the separated reference system. The PES index is defined as the ratio of the primary energy saved to the primary energy consumption of separate production. A positive value of the PES index means that cogeneration requires less primary energy than separate production. According to the EU Cogeneration Directive, this condition, PES greater than 0, is the fundamental criterion for classifying a system as high efficiency cogeneration.
Now we describe how the PES index can be evaluated in practice, following the methodology established by the EU Cogeneration Directive. The primary energy consumption of the separated reference system is calculated using harmonized reference efficiencies for conventional technologies. In particular, we introduce the electrical efficiency of a conventional power plant, eta L, SP, and the thermal efficiency of a conventional boiler, eta TH, SP, where SP stands for separate production. Using these reference efficiencies, we compute the primary energy inputs required to generate the same electrical output and useful heat as those delivered by the cogeneration unit. The total primary energy consumption of the separated system, FSP, is obtained as the sum of these two contributions. The PES index is then calculated as 1 minus the ratio between the actual fuel input of the cogeneration system and the primary energy input of the separated reference system. This formulation highlights that the PES value depends not only on the performance of the cogeneration plant, but also on the reference efficiencies adopted for separate production. For this reason, These efficiencies are defined by EU methodology and implemented through national regulations, ensuring consistency and comparability in the assessment of high efficiency cogeneration.
In this slide, we introduce the choice of the prime mover for cogeneration applications. The selection of the prime mover is a key design decision. The choice depends on key parameters: size, heat-to-power ratio, operating flexibility, fuel type. Among conventional technologies, several power plants can be used for cogeneration. Steam plants are typically adopted in large-scale industrial applications where high-temperature heat demand is available. Gas turbines are widely used in medium to large-scale CHP systems, particularly when high-quality exhaust heat can be recovered. Combined gas-steam cycles represent an extension of gas turbine systems, where exhaust heat is further exploited in a bottoming steam cycle, achieving very high overall efficiencies. Although not a prime mover in the strict sense, they are extremely important in large cogeneration plants. Internal combustion engines are commonly used in small and medium-scale applications due to their high electrical efficiency, fast response, and good part load performance. In addition to these mature technologies, innovative solutions are also available. Microturbines offer compact size, low emissions, and fuel flexibility, making them suitable for distributed generation. Fuel cells, although still limited by cost and durability, represent a highly promising technology, as they can achieve high electrical efficiency with very low emissions and silent operation. In practice, the optimal choice of the prime mover depends on several factors, including plant size, required heat-to-power ratio, operating profile, fuel availability, and economic constraints. In this slide, we examine the fields of application of cogeneration technologies as a function of electrical power output and the electric-to-thermal power ratio, also referred to as the electric index. Before interpreting the figure, it is important to note that both axes are plotted on logarithmic scales. This is a log-log diagram, meaning that equal distances on the axes correspond to orders of magnitude rather than linear increments. As a result, small visual shifts can represent large quantitative differences, especially at low power levels. The chart on the left shows how different cogeneration technologies are distributed over a wide range of electrical power outputs. The horizontal axis represents the electrical power output, while the vertical axis represents the electric index, defined as the ratio between electrical and useful thermal power. At low power levels, typically in the micro CHP and small scale range, internal combustion engines are the dominant solution. This is mainly due to their high electrical efficiency, good part load behavior, and strong operational flexibility, which make them well suited for decentralized applications. As we move toward medium power levels, industrial gas turbines become increasingly attractive. They cover a wide power range and allow flexibility in the electric-to-thermal ratio, particularly when afterburning systems are used to enhance heat production. At higher power levels, steam turbines and, above all, combined gas-steam cycles become the preferred option. These systems are typically adopted in large industrial applications, where continuous operation and high power output justify the increased complexity and capital investment. As summarized on the right-hand side, 4 main electrical size ranges can be identified. Below 5 megawatts, internal combustion engines are generally the most common choice. Between 5 and 10 megawatts, both internal combustion engines and gas turbines can be considered. Between 10 and 20 megawatts, gas turbines are usually the first option, while combined cycles may also be assessed. Above 20 megawatts, combined gas-steam cycles represent the predominant solution. Overall, this slide highlights that the choice of cogeneration technology is strongly scale-dependent and must be interpreted carefully, taking into account both the logarithmic nature of the diagram and the required balance between electrical and thermal energy outputs. In this slide, we focus on the temperature level of the recovered heat, which is a key parameter in determining the fields of application of different cogeneration technologies. In reciprocating internal combustion engines, heat recovery occurs at two distinct temperature levels. Heat recovered from the engine cooling system is available at relatively low temperatures, typically suitable for space heating or low-temperature industrial processes. In contrast, heat recovered from the exhaust gases reaches significantly higher temperatures, making it suitable for steam generation or higher temperature applications. Gas turbine systems provide the highest exhaust gas temperatures among the technologies shown, especially when post-combustion or afterburning is employed. This makes gas turbines particularly suitable for high-temperature heat demand and for integration with bottoming steam cycles. Steam turbines, on the other hand, typically deliver heat at intermediate temperature levels, which are well matched to district heating networks and medium-temperature industrial processes. Finally, combined installations, where different technologies are integrated, allow heat recovery over a wider temperature range. This increases system flexibility and enables the supply of different thermal users simultaneously. Overall, this slide highlights that the quality of recovered heat, not only its quantity, is crucial for selecting cogeneration technologies and for matching energy supply with thermal demand.
Fuel availability and emission constraints are fundamental factors in the selection of the prime mover in CHP systems. Two main aspects must be considered: the combustion mode and compliance with emission limits. Steam cycle-based CHP systems operate with external combustion and therefore offer the highest fuel flexibility. They can use a wide range of fuels, including solid fuels such as biomass and waste-derived fuels, liquid fuels such as heavy fuel oil, and gaseous fuels such as natural gas or biogas. In these systems, emission limits are mainly addressed through flue gas treatment technologies. By contrast, internally fired prime movers, such as gas turbines and combined cycle CHP systems, operate under continuous combustion conditions and are typically limited to high-quality fuels, mainly natural gas. Among reciprocating engines, spark ignition engines require gaseous or liquid fuels of medium to high quality, whereas diesel engines are more fuel flexible and can also operate on heavier liquid fuels. However, lower fuel quality generally leads to higher maintenance requirements and operating costs. These considerations show how fuel characteristics and emission constraints strongly influence the choice of the prime mover in CHP applications. In this slide, we highlight that the type of user and the final application determine the temperature level at which heat is required and therefore the appropriate heat distribution technology. Different categories of users are characterized by different thermal needs, which translate into specific temperature levels and heat transfer media. In the civil sector, where heat is mainly used for space heating and district heating, thermal demand is typically at relatively low temperatures. In these applications, pressurized water is commonly used as the heat transfer medium, with supply temperatures generally between 80 and 120 degrees Celsius. Industrial users, by contrast, are associated with higher temperature requirements linked to production processes. In these cases, heat is usually supplied in the form of steam. Typical examples include the petrochemical industry, requiring temperatures of 150 to 200 degrees Celsius, and the food and paper sectors operating at around 130 degrees Celsius. This shows how user requirements define the temperature level and guide the selection of suitable heat supply and cogeneration technologies. One of the most effective ways to exploit the thermal energy produced by a cogeneration system is district heating. Rather than using the recovered heat only locally, district heating allows this heat to be distributed to a large number of users through a dedicated network. This network consists of insulated underground pipes that carry a thermal vector fluid, typically hot water, superheated water, or steam, from a central production plant to the end users. Typical users include residential buildings, schools, hospitals, and other public or commercial facilities. A common real-world application is found in northern regions with long and cold winter seasons, such as northern Europe or northern Italy, where district heating networks serve entire cities or large university campuses. In these systems, supply water temperatures are typically in the range of 80 to 120 degrees Celsius, with return temperatures between 40 and 60 degrees Celsius, and network lengths that can extend over tens of kilometers. A single cogeneration plant can supply thermal power on the order of tens to hundreds of megawatts, significantly reducing the need for individual boilers and improving overall energy efficiency. After heat is delivered at the user substations, the fluid is returned to the same plant, forming a closed-loop system. The schematic on the left represents a typical urban district heating network, while the photograph on the right shows pre-insulated pipes, which are essential to limit thermal losses during heat transport. District heating therefore plays a key role in increasing the overall efficiency of cogeneration systems by enabling large-scale heat recovery and utilization.
This slide illustrates the evolution of energy systems as we move from large, centralized generation toward more distributed and decentralized solutions, highlighting the trade-offs between cost, emissions, and system flexibility. On the left-hand side, we see large, centralized systems, typically based on fossil fuels. These systems benefit from economies of scale and relatively low specific costs, but they are associated with high greenhouse gas emissions and limited operational flexibility. Moving toward the center of the diagram, we observe a transition to hybrid and distributed systems, where conventional generation is increasingly combined with renewable energy sources. Technologies such as cogeneration and district energy systems play an important role here, improving efficiency and reducing emissions. On the right-hand side, the figure highlights highly decentralized energy systems, dominated by renewable sources and often supported by energy storage. These solutions offer very low emissions, but introduce challenges related to intermittency, system integration, and cost. Overall, this slide emphasizes that the evolution of energy systems requires a balance between economic performance, environmental impact, and system complexity, rather than a single optimal solution. In this slide, we introduce the main typologies of CHP installation, following the design framework adopted in European guidelines. A fundamental prerequisite for implementing cogeneration is the presence of a simultaneous and sustained demand for both electrical energy and useful thermal energy at a temperature level compatible with the quality of heat that can be recovered from the CHP unit. Once this condition is satisfied, the first key design decision concerns how the system is sized in order to meet the user's energy demand. In practice, this choice is between sizing the CHP unit based on the electrical load or sizing it based on the thermal load. These two approaches are commonly referred to as power-led CHP or imposed electrical load, and heat-led CHP, or imposed thermal load. The selected sizing strategy has a direct impact on the primary energy saving index, and therefore on whether the system can be classified as high-efficiency CHP under EU legislation. In the next slide, we will examine these two configurations in more detail.
First of all, we introduce the energy plane, which is a useful graphical tool for representing CHP operation. On this plane, the horizontal axis represents the electrical energy output, E, while the vertical axis represents the useful thermal energy, Q, in accordance with European Union definitions. Each point on the plane corresponds to a specific combination of electrical and thermal energy. The green point represents the user's energy demand, while the red point represents the energy output of the CHP unit. The straight line passing through the origin represents the characteristic of the CHP system, showing the coupling between electricity and useful heat production. The angle theta defines the ratio between thermal and electrical energy, with its tangent equal to Q over E. This quantity represents the inverse of the electricity to heat ratio of the CHP system. By comparing the position of the user demand with the CHP operating characteristic, this representation allows us to visually assess load matching operating strategy and the suitability of heat-led or power-led operation.
In this slide, we build on the energy plane representation to introduce the concept of degrees of freedom in CHP systems. Depending on their structure and level of complexity, cogeneration plants can operate at different combinations of electrical and thermal load, which translates into different regions of the QE plane. A system with 0 degrees of freedom operates at a single fixed point. Both electrical and thermal outputs are fixed and cannot be adjusted. In a system with 1 degree of freedom, for each value of electrical output E, there corresponds only one value of thermal output Q. This indicates a strong coupling between electricity and heat, typical of many conventional CHP units. Systems with 2 degrees of freedom exhibit the highest operational flexibility. For a given electrical output, a range of thermal outputs is possible, meaning the operating point can move within an area of the energy plane. This greater flexibility allows better adaptation to variations in user demand and facilitates both heat-led and power-led operation, which is particularly important for maximizing heat utilization and primary energy savings. Now we summarize the main design criteria for assessing the feasibility of a CHP system. The implementation of cogeneration always requires a careful technical and economic assessment. This assessment must start from a detailed analysis of the user's energy demand profiles, considering both electrical and thermal loads and their evolution over time. At the same time, the available prime mover technologies must be evaluated, since different users may be better matched with different CHP solutions. From an economic perspective, the analysis should focus on the cost of the produced energy, electricity and useful heat, and on the expected annual operating hours of the plant. Finally, the most appropriate operating strategy, whether heat-led, power-led, or mixed, cannot be defined a priori, but must be determined on a case-by-case basis, depending on user demand and operating conditions. The energy audit is absolutely necessary in CHP sizing and should be focused on daily load profiles and annual profiles. The energy audit is a fundamental step in CHP design, as it provides detailed information on how electrical and thermal demands vary during the day under different operating conditions. The figure shows how hourly load profile of a hypothetical user vary on a typical winter working day. The electrical demand starts to increase around 6 a.m. at the beginning of the daily activities and then remains nearly constant through the day. In contrast, the thermal demand, mainly associated with the space heating, reaches its maximum around 8 a.m. when indoor spaces are brought to comfort temperature, and then gradually decreases, stabilizing during the rest of the day. These daily profiles are essential for understanding load simultaneously and for selecting an appropriate CHP operating strategy. It is also necessary to extend the energy audit to annual load profiles. The figure shows the annual curve of average electrical and thermal loads for the same hypothetical user of the previous slide. In addition to seasonal variations, it is possible to identify a base load for both electricity and heat, indicated by the dashed lines. This base load represents the minimum continuous demand over the year and plays a key role in CHP design. In practice, cogeneration systems are often sized to cover the base load rather than peak demand in order to maximize operating hours. Sizing the CHP unit on the base load typically results in more stable operation, higher utilization of the system, and improved economic performance.
Now, we compare heat-led and power-led CHP systems and highlight their main operational implications. When a CHP system is sized according to thermal demand, the configuration is known as heat-led CHP. In this case, the cogeneration unit is designed to maximize the utilization of recoverable heat, ensuring that the user's thermal demand is fully met. Any additional electrical energy required is supplied by the electricity grid, while excess electrical production may be exported, exchanged, or sold. This configuration generally results in high thermal utilization and is often favorable for achieving high primary energy savings. Conversely, when the system is sized according to electrical demand, the configuration is referred to as power-led CHP. Here, the CHP unit follows the user's electricity consumption profile. Residual thermal demand must be covered by conventional thermal technologies, such as auxiliary boilers. Moreover, if recoverable heat exceeds the instantaneous thermal demand, part of the available heat may remain unused unless thermal storage or additional heat sinks are available. As a consequence, power-led CHP systems may lead to lower overall heat utilization and reduced primary energy savings, especially in applications with limited or highly variable thermal demand. For this reason, EU design guidelines stress the importance of carefully analyzing thermal load profiles when adopting a power-led approach.
We begin with the ideal CHP operating condition. In this case, the operating point of the CHP unit exactly coincides with the user's energy demand. Both the electrical demand and the thermal demand are fully covered by the CHP unit without the need for interaction with the electricity grid or auxiliary thermal systems. In the QE plane, this condition is represented by the overlap between the user demand point and the CHP operating point along the system characteristic. This represents the reference case corresponding to perfect load matching, maximum heat utilization, and the highest potential primary energy savings.
We now consider power-led CHP operation. In this configuration, the CHP unit is sized to meet the electrical demand of the user. The electrical load therefore determines the operating point of the system. The corresponding thermal output, indicated as Q prime, is a consequence of the CHP characteristic and may be insufficient to meet the total thermal demand. The residual thermal demand, Q double prime, must then be supplied by an auxiliary boiler. In the QE plane, this situation is represented by a vertical mismatch between the user's thermal demand and the CHP thermal output. In this slide, we consider a specific power-led CHP operating condition in which part of the recoverable heat cannot be utilized and is therefore rejected to the environment. As in all power-led configurations, the CHP unit is sized to meet the user's electrical demand, and the electrical load determines the operating point of the system. At this operating point, the corresponding thermal output of the CHP unit is greater than the user's thermal demand. Only part of the available heat is delivered to the thermal load, while the remaining share, indicated as Q double prime, is rejected to the ambient as waste heat. This condition represents an unfavorable operating mode, since unused recoverable heat leads to lower overall heat utilization and a reduction in the primary energy saving index. For this reason, EU CHP design guidelines recommend avoiding such operating conditions whenever possible through appropriate sizing, thermal storage, or additional heat sinks. We now move to heat-led CHP operation with an electrical deficit. In this case, the system is sized according to thermal demand, and the thermal load fixes the operating point of the CHP unit. The corresponding electrical output, E prime, is determined by the CHP characteristic and may be lower than the user's electrical demand. The remaining electrical demand, E double prime, is therefore supplied by the external electricity grid. This configuration typically ensures high heat utilization and is common in applications with a strong and continuous thermal demand. Finally, we consider heat-led CHP operation with an electricity surplus. As in the previous case, the thermal demand determines the operating point of the CHP unit. However, here, the associated electrical production exceeds the user's electrical demand. The surplus electricity, indicated as E prime, is exported to the electricity grid through sale or exchange mechanisms. In the QE plane, this condition is shown by the CHP operating point lying to the right of the user demand point, while maintaining full coverage of the thermal load. To conclude, it is important to emphasize that CHP systems can operate under different operating modes, such as heat-led or power-led operation, depending on the chosen sizing strategy and on the characteristics of the user demand. According to European CHP directives and the associated assessment methodologies, the qualification of a cogeneration system as high-efficiency CHP cannot be based on instantaneous or partial operating conditions alone. Instead, the Primary Energy Saving Index, or PES, must be evaluated by considering the total primary energy consumption and savings over the entire year. This annual assessment must account for all operating regimes, for variations in electrical and thermal demand, and for periods of heat deficit, heat surplus, or heat rejection. Only an annual integrated assessment of energy consumption and energy savings provides a reliable basis for comparing CHP with separate production, for assessing the real efficiency benefits, and for ensuring compliance with European high-efficiency CHP criteria.
In this section, we introduce the main CHP plant technologies. They are most widely used in practice. We will focus on steam plant-based CHP plants, gas turbines, CHP plants, combined cycle CHP plants, and internal combustion engines CHP plants. For each technology, we will discuss the basic operating principles, the electricity to heat ratio, and the operating flexibility, as well as typical application fields and sites ranges. This overview will provide a foundation for understanding how different CHP technologies affect the system performance and the potential to achieve high primary energy savings in accordance with the EU CHP guidelines.
Initially, our focus is on cogeneration systems based on steam power plants. Steam plants operate according to the Rankine cycle and are one of the most well-established cogeneration technologies, particularly for medium to large scale applications. There are two main categories. The first category comprises plants with the total steam extraction. Also known as back pressure steam plants, which deliver the exhaust steam to the thermal user. The second category comprises plants with partial steam extraction, where only some part of the steam is extracted and delivered to the final thermal user, while the rest, the remaining part of the steam flow expands in the turbine and condenses. In all cases, the mechanical power produced at the turbine shaft drives an electric generator, and the steam generator can be supplied by a variety of heat sources, such as fossil fuels, biomass, and municipal solid waste. This flexibility in the fuel's choice makes steam-based CHP plants attractive from economic and environmental perspectives. Here we can see the main configurations of steam power plants used for cogeneration. Starting from the left, we can see the conventional steam power plant without cogeneration. In this case, all the steam expands to the condenser and no useful heat is recovered. The second configuration is the back pressure steam plant, where all the exhaust steam exiting from the turbine is directly supplied to the thermal user, ensuring full heat recovery but limited flexibility. The third configuration is the extraction steam plant, in which part of the steam is extracted and at an intermediate pressure for thermal user, while the remaining steam expands further and is condensed. This layout offers greater operational flexibility and could be considered a 2 degrees of freedom system. Finally, the extraction and back pressure steam plant combines both concepts, allowing steam extraction for thermal use and back pressure operation, and therefore providing the highest degree of flexibility among steam-based CHP plants. These different configurations differ in electricity to heat ratio, degrees of freedom, and suitability for heat-led or power-led operation, which will be discussed in the following slides.
Copenhill, also known as Amagabage, is a flagship example of a waste-to-energy combined heat and power plant integrated into an urban district heating network. The plant uses municipal solid waste as fuel to produce electricity and supply heat to Copenhagen's district heating system, achieving high overall efficiency and significant reductions in landfill disposal. Beyond its energy function, Copenhill is also an iconic example of sustainable design, combining industrial infrastructure with public spaces, and demonstrating how CHP plants can play a key role in circular economy and urban energy systems. Steam-based cogeneration plants operate with external combustion and are classified under the EU framework as CHP systems, producing both electricity and useful heat. They typically cover installed electrical capacities from a few megawatts up to several tens of megawatts and can be configured with back pressure or extraction steam turbines. Thanks to external combustion, these plants offer high fuel flexibility. Their overall efficiency, expressed through the energy utilization factor, can reach values between 60 and 85%, while electrical efficiency typically ranges from 20 to 35%. The resulting power to heat ratio vary from 0 to 50% and depends on the operating mode and the degree of heat extraction. To conclude, steam-based CHP plants represent a well-established and reliable cogeneration technology, especially for medium and large-scale installations. Their main advantage is the high fuel flexibility and the possibility of supplying thermal energy in the form of steam at different pressure and temperature levels, which makes them particularly suitable for industrial users and district heating networks. On the other hand, steam CHP plants are characterized by large dimensions and slow response to load variations, and electrical output decreases when heat is extracted for cogeneration. For these reasons, they are best applied where thermal demand is stable and continuous and where long operating hours can be ensured, allowing high efficiency and significant primary energy savings in accordance with EU CHP guidelines.
We now focus on cogeneration systems based on gas turbines, which are the most widely used prime movers for medium to large-scale CHP applications, typically in the range from 1 to 100 megawatts of electrical power. A key characteristic is the high temperature of the exhaust gases, generally between 350 and 500 degrees Celsius. In addition, the exhaust still contains a significant amount of oxygen, typically between 16 and 18%. This allows the exhaust gases to act as an oxidizer in a post-combustion boiler, where additional fuel can be burned to increase the available thermal energy. As a result, the recovered heat is available at a high thermal level, making gas turbine cogeneration suitable for high-temperature applications such as industrial processes or steam production. Now, we analyze cogeneration systems based on gas turbines, focusing on the schematic layout and on the role of post-combustion, also referred to as supplementary firing. Starting from the left side of the diagram, the gas turbine converts the chemical energy of the fuel into electrical power, which is delivered through the generator. At the same time, the turbine releases exhaust gases at relatively high temperatures, typically in the range of 450 to 550 degrees Celsius. These temperature levels are already sufficiently high to allow high-pressure steam production in a heat recovery steam generator. The exhaust gases are then directed to the heat recovery boiler, where thermal energy is transferred to water, producing steam or hot water for the thermal user. The presence of a steam drum indicates that this configuration is suitable for the production of saturated or superheated steam, depending on the application. A key feature of this system is the possibility of post-combustion, implemented through a duct burner installed in the exhaust gas stream. Thanks to the residual oxygen content in the turbine exhaust, additional fuel can be burned without the need for extra air, increasing the gas temperature to values that can exceed 1,000 degrees Celsius. This allows a significant increase in the thermal output, while the electrical power produced by the gas turbine remains essentially unchanged. As a result, the thermal to electrical ratio, which typically lies between about 1.5 to 1 and 3 to 1, can be further increased, depending on the operating conditions and the turbine characteristics. An important aspect to note is that the efficiency of post-combustion is very high, often exceeding 95%, and in some definitions, it may even appear greater than 1, because additional useful heat is produced without increasing electrical losses. Overall, gas turbine cogeneration with post-combustion offers remarkable operational flexibility, making it particularly suitable for applications with variable thermal loads or high-temperature heat demand, such as industrial processes and steam distribution networks. In this slide, we focus on the afterburner, also known as the post-combustion system, and on its impact on the
Gas
thermal
turbine-based
performance of a gas
cogeneration
turbine
systems are
cogeneration
widely
plant.
used for medium to
Post-combustion is
large-scale
characterized by an
applications
additional fuel
because they
consumption in
offer
the exhaust gas
flexibility and
stream,
high
which leads to an
performance.
increase in the
These
available
plants
thermal
typically
output
operate in the
compared to the
range
unfired
of
configuration.
0.2 to
For this
100
reason, it is
megawatts
meaningful to
of
define a
electrical capacity,
post-combustion
and
efficiency,
sometimes
which relates
even
the
higher
additional
for
useful
industrial
thermal
or
production to the
utility-scale
energy input of the duct
installations.
burner.
The most
This
common
efficiency is
configuration
defined as
is
the
an open
ratio between the
cycle gas
incremental thermal
turbine
power,
combined with
indicated
a
as
heat
delta
recovery
Q dot
system.
sub Pc, and the fuel
Here,
energy
the
input,
exhaust gases
E
are
dot
used
sub
to
Pc.
produce a useful
Let us
heat
now interpret the
through a heat
T-Q
recovery boiler.
diagram shown on the right-hand
The main
side.
components
The
include
diagram represents
the
the temperature
compressor, the
heat
compressor
transfer
chamber,
behavior
the
of the heat
turbine, and
recovery
the
steam
heat recovery
generator,
boiler.
both with and without
It is
post-combustion.
a system
If the pinch point
versatile
temperature difference
for
remains constant,
fuel
the introduction of
options that
post-combustion
can
causes
be
a
natural
rotation of the
gas,
gas cooling line in the
LPG,
TQ plane,
biogas,
resulting in a steeper
biofuels,
slope.
emitting gas
This behavior
even
reflects the
like
higher
liquid
thermal level of
fuels.
the exhaust gases
Now,
upstream of the
let's talk
high-pressure
about
evaporator.
performance.
The
The
consequences are
energy
twofold.
utilization
First,
factor
the steam
typically
production in the
ranges from
high-pressure
60 to
evaporator increases
85%.
due to the higher temperature
Electrical
driving force.
efficiency varies
Second,
between
the exhaust
22 and
gas temperature at the stack
37%,
decreases, leading to an
depending
improvement
on
in the
turbine
overall
size
heat
and
recovery
operating
efficiency of the
conditions.
boiler.
Finally, the
Overall,
power to
this
heat
slide
ratio
highlights
is
that
generally between
post-combustion not only
0.5 and
increases the thermal
1.1,
output, but can also
influenced by
improve the
turbine
effectiveness of
design
heat
and heat
recovery,
recovery
making it a powerful
configuration.
tool for enhancing flexibility
In this
and
slide,
performance
we
in gas
summarize the
turbine
main
cogeneration
advantages
systems.
and limitations of gas turbine-based CHP plants. Among the main advantages, gas turbine CHP systems are characterized by relatively low initial investment costs, high availability, and good values of the main performance indicators. They can be installed in relatively short times, provide useful thermal energy at high temperature, and show a very fast response to load variations, which makes them suitable for applications with variable demand. On the other hand, gas turbine CHP plants require periodic inspections and scheduled overhauls due to operation under high thermal and mechanical stresses, and they need specialized personnel for correct operation. They are also less suitable for very frequent start-stop operation and generally require liquid or gaseous fuels in open cycle configurations. Typical installation times range from 9 to 14 months, while the expected service life is about 15 to 20 years. This slide summarizes cogeneration systems based on the steam injected gas turbine or STIG cycle. First, regarding the operating principle, steam produced in the heat recovery steam generator is partly directed to thermal user, while when there is not request of heat, steam is directly injected into the gas turbine combustor. This increases the mass flow through the turbine and therefore raises the electrical power output. When required, a duct burner or post-combustion system can be added downstream to further increase STM productant for thermal users. In terms of performance, STIG systems offer good electrical efficiency compared to simple cycle gas turbines and allow the production of high pressure steam. An important feature is the flexibility of the thermal to electric ratio, which can be controlled by regulating the steam injection rate. Typical operating values include exhaust gas temperatures between 450 and 550 degrees Celsius, steam injection rates of about 5 to 20% of the compressor air flow, electrical efficiencies in the range of 35 to 42%, and overall cogeneration efficiencies up to about 85%. From an environmental standpoint, steam injection lowers combustion temperature and is effective in reducing NOx emissions, often in combination with additional emission control systems. Finally, from a current technological perspective, STIG systems are mainly found in legacy CHP plants. They are rarely adopted today, having been largely replaced by combined cycle systems or gas turbines with HRSG and supplementary firing due to high water consumption, reduced heat recovery, and increased system complexity. A combined cycle gas turbine plant qualifies as cogeneration or CHP when useful thermal energy is supplied to an external user by controlled steam extraction from the steam turbine, in addition to electricity generation from both the gas and steam turbines. In this configuration, the steam cycle is typically arranged as a condensing turbine with controlled extraction. This layout provides operational flexibility and allows the plant to comply with high-efficiency CHP criteria, which are assessed on an annual basis through the Primary Energy Savings, or PES, indicator. Let us now briefly focus on the CCGT scheme shown in the diagram. The system consists of a gas turbine which produces electrical power and discharges high-temperature exhaust gases into the Heat Recovery Steam Generator, or HRSG. Inside the HRSG, thermal energy from the exhaust gases is recovered to generate steam at different pressure and temperature levels, feeding the steam turbine and, at the same time, allowing controlled steam extraction for thermal users. The remaining steam expands through the turbine and is then condensed in the condenser, closing the water-steam cycle with make-up water supplied to compensate for losses. This layout enables a cascade use of energy. High-temperature energy is first converted into electricity, while lower-temperature heat is recovered as useful thermal energy, maximizing overall efficiency and supporting compliance with high-efficiency CHP criteria. An important aspect of this CCGT configuration is that even in the absence of a thermal load, for instance for district heating during summer season, the plant maintains a very high electrical efficiency. This is because the exhaust heat from the gas turbine is already recovered in the steam cycle and converted into additional electrical power, rather than being rejected to the environment. As a result, when no steam is extracted for cogeneration, there is no significant quantity of heat that could otherwise be converted into useful energy. This distinguishes CCGT plants from many other CHP technologies, where the absence of thermal demand would lead to heat rejection and efficiency penalties. From an application standpoint, this technology is widely applied in large-scale CHP systems, such as district heating networks and energy-intensive industries, where a sustained demand for both electricity and high-quality heat is available. Today, new deployments are mainly driven by repowering of existing plants, the expansion of district heating systems, and decarbonization pathways, while high capital costs generally limit this solution to medium and large-scale applications. This video shows a combined cycle gas turbine power plant operating in cogeneration mode with district heating. The plant produces electricity at very high efficiency, while recovering part of the steam cycle thermal output to supply a large urban heating network. It is a representative example of large-scale, high-efficiency CHP, where electricity generation and district heating are effectively integrated to maximize primary energy savings and reduce environmental impact.
We now introduce cogeneration with internal combustion engines, one of the most widely used CHP technologies. ICE-based CHP systems are particularly attractive due to their high electrical efficiency, operational flexibility, and wide availability across different power ranges. The main heat recovery sources are the engine cooling system and the exhaust gases, which together allow the recovery of a significant fraction of the fuel energy as useful heat. In terms of fuel flexibility, spark ignition engines typically operate on natural gas or biogas, while compression ignition engines can use diesel or biodiesel, and are often preferred in applications requiring very high reliability. Typical applications include critical users, such as hospitals, where continuity of electricity supply is essential and on-site generation provides additional resilience. Recovered thermal energy can be used for direct hot water production, chilled water generation via absorption chillers, or clean steam production for various thermal users. Let us now look at the technical characteristics of ice-based CHP plants. The installed electrical capacity typically ranges from 10 kilowatts up to about 5 megawatts, covering micro CHP as well as small and medium-scale CHP applications. Two main engine configurations are used: spark ignition engines and compression ignition engines, depending on fuel type, operating profile, and emission constraints. The core plant components consist of an internal combustion engine coupled to an electric generator, and heat recovery systems connected to the engine cooling circuits and exhaust gases. ICE CHP plants can operate on a wide range of fuels, including natural gas, biogas, and syngas, as well as liquid fuels such as diesel, biodiesel, or methanol. Overall efficiencies, expressed through the energy utilization factor, typically range between 70 and 90%, while electrical efficiency alone reaches values of 30 to 45%, which are particularly high for decentralized generation systems. The resulting power-to-heat ratio between 0.4 and 1 is generally higher than that of steam-based CHP systems. Finally, let us summarize the main advantages and limitations of ICE-based CHP plants. Among the key advantages, ICE CHP systems offer high availability and reliability, high electrical efficiency with favorable EUF values, and a wide range of unit sizes, including micro-cogeneration. They are characterized by a fast, dynamic response, good load-following capability, and the possibility of frequent start-stop operation, which makes them well-suited to variable demand profiles. Additional advantages include short installation times and modular configurations, allowing efficiency to be maintained even under partial load operation. On the other hand, ICE CHP plants also present some limitations. These include noise and vibration issues, especially for diesel engines, stringent fuel quality requirements, and high NOx emissions, which require appropriate emission control systems. Moreover, the recovered heat is mainly available at low to medium temperature levels, which limits the suitability of ICE CHP plants for high-temperature industrial processes. In terms of life cycle, small units typically operate for 10 to 30,000 hours, while large units have lifetimes of 15 to 20 years.
We now examine the potential heat sources that can be exploited for cogeneration in internal combustion engines. In ICE-based CHP systems, there are four main sources of recoverable thermal energy. The most important heat source is represented by the exhaust gases. These constitute the thermodynamically most valuable heat stream because they are available at relatively high temperatures, typically between 400 and 500 degrees Celsius. As a result, exhaust heat can be used not only for hot water production, but also for the generation of medium pressure steam when required by the application. A second relevant heat source is the engine cooling water, also known as jacket water. In this case, the heat is available at temperatures below 100 degrees Celsius and is therefore mainly suitable for hot water production and low-temperature thermal uses. Additional heat can be recovered from the lubricating oil cooling system. This heat is also available at relatively low temperatures, typically between 75 and 90 degrees Celsius, and is usually combined with jacket water heat in practical CHP installations. A further contribution, present only in turbocharged engines, comes from the charge or boost air. To reduce the compression work in the cylinders, the intake air supplied by the turbocharger is cooled down to approximately 60 to 80 degrees Celsius, making a limited amount of low-temperature heat recoverable. It is important to note that when exhaust gas temperatures fall below approximately 140 degrees Celsius, condensation of acidic compounds may occur, which limits the possibility of extending heat recovery to lower temperature levels. Finally, a fraction of the thermal energy, typically less than 10% of the fuel energy input, is unavoidably dissipated to the environment through radiative heat losses. This slide illustrates how the fuel energy input is divided between electricity, recoverable heat streams, and losses in modern internal combustion engine CHP units. The comparison is based on Sankey diagrams for two representative engine sizes. On the left, we consider a 1 to 2 megawatt electric gas engine, representative of medium-sized CHP units. In this case, approximately 39% of the fuel energy is converted into electricity. About 26% is available as high-temperature exhaust heat, while roughly 17% is recovered from the cooling circuits, including jacket water and lubricating oil. A smaller fraction, around 5%, is associated with charge air cooling, and the remaining 13% corresponds to losses. On the right, we observe a large lean burn gas engine in the range of 4 to 5 megawatts electric. Here, the electrical efficiency is higher, reaching approximately 44%. As a consequence, the amount of recoverable heat is reduced. Exhaust heat decreases to about 22%, cooling-related heat to roughly 15%, and charge air heat to around 4%, while total losses are reduced to approximately 8%. This comparison highlights a fundamental trade-off in ICE-based CHP systems. As electrical efficiency increases, both the quantity and the quality of recoverable heat tend to decrease, while overall losses are minimized. For this reason, medium-size engines offer greater flexibility, including limited steam or high-temperature hot water production, whereas large, highly efficient engines are particularly well suited for district heating applications, where heat is mainly required at hot water temperature levels.
We now turn to the environmental aspects of cogeneration systems based on internal combustion engines. High-power internal combustion engines (CHP) plants, particularly those using compression ignition or diesel engines, and in some cases also spark ignition engines, may present environmental and acoustic challenges, especially when installed in urban areas or densely populated locations. According to the EU environmental and noise regulations, such as the Industrial Emission Directive and the Environmental Noise Directive, the environmental assessment of ICE CHP plants must explicitly address three main aspects. First, exhaust emissions, which are strictly linked to the fuel type and to the emission control systems adopted, such as catalytic converters, particulate filters, or SCR systems. The SCR means selective catalytic reactors. Second, noise emissions, both airborne and structure-borne, which require carefully acoustic design and mitigation measures. Third, mechanical vibrations, which may be transmitted to surrounding buildings and infrastructure if not properly isolated.
We now consider the main pollutant emissions associated with CHP systems based on internal combustion engines. The principal regulated pollutants are nitrogen oxides, or NOx, which represent the primary environmental concern because they are mainly formed at high combustion temperatures. Other relevant pollutants include carbon monoxide, produced by incomplete combustion, volatile organic compounds, or VOCs, originating from unburned or partially burned fuel, and particulate matter, which is mainly relevant for diesel engines. Emission characteristics strongly depend on the engine type. Lean burn natural gas engines exhibit the lowest engine-out NOx emissions, typically between 25 and 75 parts per million, corresponding to approximately 0.7 to 3 grams per kilowatt hour. Compared to rich burn engines, they generally show higher carbon monoxide and VOC emissions, but very low particulate emissions. Rich burn, stoichiometric natural gas engines produce much higher engine-out NOx, often in the range of 300 to 1,500 parts per million. For this reason, they require catalytic aftertreatment, typically a three-way catalyst, in order to meet regulatory emission limits. Diesel engines present the most critical emission profile. They typically produce NOx levels 5 to 20 times higher than lean burn gas engines, often exceeding 20 grams per kilowatt hour, together with significant particulate emissions. On the other hand, diesel engines usually exhibit lower carbon monoxide emissions than gas engines. In practice, modern stationary diesel CHP units installed in regulated contexts are equipped with oxidation catalysts, diesel particulate filters, and selective catalytic reduction systems, similarly to modern diesel vehicles. Finally, it is important to emphasize that there is no direct regulatory limit on carbon dioxide emissions for CHP engines. CO2 emissions are regulated indirectly through emissions trading, carbon pricing mechanisms, and efficiency-based criteria, such as the Primary Energy Savings Index used to define high-efficiency CHP. To control these emissions, ICE CHP systems rely on a combination of in-cylinder control techniques and post-combustion exhaust treatment. In-cylinder control strategies include lean burn combustion, where excess air lowers the flame temperature and therefore reduces NOx formation, as well as ignition timing retard, fuel injection control, exhaust gas recirculation, or EGR, and water or humid air injection. Turbocharging combined with charge air cooling is also used to maintain efficiency while limiting emissions. The main benefit of these techniques is lower engine-out NOx, but they may introduce efficiency penalties or increased CO and VOC emissions if combustion becomes excessively lean. Post-combustion exhaust treatment provides further emission reduction. Three-way catalysts, or NSCR systems, are used for rich burn gas engines, achieving about 90% reduction of NOx and CO, and around 80% reduction of VOCs. Oxidation catalysts are applied to lean burn gas and diesel engines, mainly to reduce CO and VOC emissions. Selective catalytic reduction, or SCR, is required for ultra-low NOx limits, providing 80 to 95% NOx reduction. For diesel engines, diesel particulate filters, or DPF, are used to achieve about 90% reduction in particulate matter. With modern emission control systems, CHP gas engines can achieve NOx levels around 0.07 pounds per megawatt hour, and CO levels around 0.2 pounds per megawatt hour, while still maintaining electrical efficiencies above 40%, demonstrating that high efficiency and low emissions can be achieved simultaneously.
This slide shows a practical example of a containerized CHP unit based on an internal combustion engine, specifically the Ecomax natural gas system by AB Holding. For further details on the technical layout and system components, you are suggested to consult the manufacturer's website and the linked video, which provide a clear and comprehensive overview of a real industrial CHP installation.
To conclude this section, we can highlight a few key points regarding CHP systems based on internal combustion engines. Cogeneration allows the simultaneous production of electricity and useful heat, leading to a significant improvement in overall energy efficiency compared to separate generation. Internal combustion engines are particularly well suited for micro and small scale CHP applications thanks to their high electrical efficiency, fast dynamic response, and wide availability. The main recoverable heat sources include exhaust gases, which provide the highest temperature level, as well as the engine cooling circuits, lubricating oil, and charge air. When these heat sources are properly exploited, ICE-based CHP systems can achieve very high energy utilization factors, often exceeding 70%, making them ideal for applications with continuous and simultaneous heat and power demand. From a design and operational perspective, the effectiveness of CHP systems strongly depends on matching the plant to the user's energy demand. In particular, the simultaneity of thermal and electrical loads and the choice between heat-led or power-led operation play a crucial role in determining overall efficiency and primary energy savings. According to European regulations, the performance of a cogeneration system must be evaluated on an annual basis using the primary energy saving index, rather than considering isolated operating conditions. Internal combustion engine CHP plants offer high flexibility, modularity, and relatively short installation times, while remaining compatible with both conventional and renewable fuels such as biogas. Finally, environmental aspects are essential. Appropriate emission control technologies are required to ensure compliance with regulations, making ICE-based CHP a mature and sustainable solution for decentralized energy systems.